That looks good.
All right, audio working well?
Audio sounds good.
Okay.
It's now 15 after again, so I think we will just hand it over to you, Mark, and let you proceed with your topic on DC-DC converters and EMC troubleshooting.
All right, well, welcome everyone to the session on EMC troubleshooting. I'll be going over a little bit of just basics of design and how it impacts EMC in general to kind of help with our understanding both in the design phase as well as when we get to the lab and we have trouble, how we want to think about tackling these problems. So my name is Mark Malik. I'm based out of the Livonia, Michigan office for MPS, where the EMC lab is located. I support OEM and Tier 1 customers, mostly in automotive. Have about 20 years of experience both at the OEM level, system level design, as well as hardware design for automotive and military. Been doing field application support for quite some time now. A lot with power supply design, obviously, as well as high-speed communication links. I love doing electronics. It's something I do in my spare time, and I have a lot of projects in the background, so it's something I like to do outside of work. Along with, I have 2 wonderful kids and a wife that enjoy spending time with, and as well, I like doing snowboarding. And that picture on the left looks like I had a pretty good cold, snowy day there on the mountain. So that's another thing that I really enjoy doing. Really quick, just an agenda in terms of what we're going to cover in the next 30-ish minutes. Kind of an approach to troubleshooting, how we want to think about things before we get into maybe trying to apply band-aids, how to have a structured approach to think about these issues and tackle them. We're also going to talk about the tools we use to do troubleshooting, to look at various aspects of conducted radiated emissions. I'll touch on immunity, but that's not something I'm going to cover in too much depth in this discussion. I'm going to go over some basics on how to make electrons behave. Obviously, if they're behaving the way we want them to, we're going to have a good day in the lab, but that's always kind of how I think about tackling some of these problems in terms of how they aren't doing what I want them to do, or how to make them do what we want them to do. I'm going to cover some examples on MPS evaluation boards and walk through some of those. And like I mentioned at the end of Francesca's presentation, I'm going to go over some inductor impact on EMC. I know that Francesca's covered that in some aspects with respect to starter winding, ground around the inductor and underneath the inductor, but we'll look at that in a little bit different light as well. So in terms of troubleshooting, we need to start with, obviously, what's the basic problem here? Are we failing radiated or conducted emissions? Is an immunity problem? And we can kind of think about those two as inverses of each other in rough terms. What is the test setup like? So do we have an incoming harness for power, obviously, for our modules? Do we have signal lines coming out? Are we also sending power off board? That's something we'll have to take a look at. Is the housing metal or plastic? Obviously, that may or may not help us. This picture we have in the upper right, it's kind of tough to see, but there's openings around these connectors here. And depending on what is going on the other side of that, this can become a slot antenna and cause problems for us. So this is not necessarily a good shield being inside a metal enclosure. So we need to think about what's going on behind that portion of it, or even in other areas of the circuit. Mentioned cables connected to the system. We got a picture here of a EVB where we would have power coming in and an enable signal. We're also sending power out. This could be representative of your system, and we need to consider both the input side and output side if that is the function of the module. At what frequencies do we exceed the limits? We'll go through a little bit of a structured approach on that, both in terms of design and troubleshooting, looking at frequencies. And is it possible to identify clock sources? We'll also take a look at that in more of a detailed approach, a structured approach, how we can look at that in detail. And where are the DC to DC converters placed? Ideally, what we would like to do is if this is the connector on this EVB, we'd like to have the DC to DC placed all the way over here. Obviously, physical limitations and design of the product may not allow for that because we want to keep things away from noisy sources where we could have a path coupling back to the input, bypassing any type of filtering that we put on the board, and we'll take a look at that. So in terms of looking at specific elements of our EMC countermeasures or design, do we have filter elements placed at each cable, both the input and the output? What is the distance from the DC to DC converter to the cable or connector, right? And depending on the test setup, I would say this is not a good test setup where we've got a connector and we're routing around over top the converter underneath the board and then on to the Lizens in the test setup. You know, obviously we are putting the harness pretty close to the DC to DC power supply. We could be offering an easy path for things to couple to. So we need to think about, is this reality in the vehicle? Is this a good test setup? And think through it. It should be realistic, but it should not be more difficult than it needs to be. Identify and mark all high dB/dt nodes and DIDT nodes. I think we've taken a look at that in some of the previous presentations, but we'll take a look at some waveforms as well, just to reiterate that. Check the routing of all those circuits. Francesca's touched on that as well, and some ideas that we've had to maybe help with that or identify what are the best practices there. But obviously, these are critical things we need to look at. Use snap-on ferrites for cables to distinguish common mode and differential mode noise. Obviously, when we go to production, using the ferrites is not going to be feasible in most cases, but this can be an effective troubleshooting method in the lab. And the ferrites essentially are creating high impedance to those frequencies higher up. You need to select the ferrites based on whatever band you're looking at. There are different ones, different types, but they are a useful troubleshooting tool. And obviously placing shielding over the DC to DC converter block or other areas where you may suspect issues. As far as tools that you can use, copper foil, we just talked about shielding. This is one very easy way to create a shield around areas or large areas, small areas, it doesn't matter, depending on what you want to achieve when you're doing your troubleshooting. This is very low cost and versatile, but I would caution you that versatile is maybe not necessarily good, because if you cover a large area, you may not be narrowing in on what the actual problem area is. But obviously you can create smaller and smaller shields or more targeted shields and narrow things down a bit. The snap-on ferrites, mentioned those as well. So we're trying to create high impedance to high frequency signals traveling along cable, typically in common mode. This is a low cost thing. It's not as versatile, but it is going to rule out a very specific thing. So if we snap on a ferrite and our emissions change in a very positive way, we've very quickly narrowed in on what our issue is, and now we need to figure out the path that noise is coming from. Field probes. Field probes can be used both in the lab as well as on the bench. These things can be generally connected to your oscilloscope depending on its capability. Things like bandwidth would be important. But these probes can be used to identify where field strength is high. Just keep in mind, you can identify areas where we are generating fields, but that may not necessarily be the source of the issue. So just because you found one area of high field strength, you may have to check all over the board. And in particular, that one specific area might not be the problem. It might be a different area, but it does help identify these things. These are more medium cost. Kits are more in the hundreds of dollars. Individual probes could be less than that, and they are pretty versatile. You can use them at the bench. You can use them in the lab. You can use them with an oscilloscope. You can also use them with a spectrum analyzer. Current probes, they can be used with a spectrum analyzer, typically very, very specialized equipment. They're higher cost. can be as much as in the $1,000 range. Not as versatile, but they do very quickly narrow in on these different modes of noise that we would be having in the harness and the power supply side. So here's an example of using copper foil. On the top side here, we've got a shield wrapped over the inductor towards the power supply, kind of covering the input caps as well to some extent, and then tied to the ground on the board. So we're trying to capture any E field emitted and return it back to ground quickly. We want all of the charge to stay on the board, all the energy to stay on the board and leave out the way it came in, and that will greatly improve our radiated emissions and conducted emissions. And here, we'll take a look at this example later. You know, we're covering a large area. In this case, you're gonna be covering a lot of things depending on what's going on your board, but this is something that can be done with the copper foil. We can cover large areas, we can cover small areas. Very useful tool that way. This is an example of the snap-on ferrites. They come in different shapes and sizes. You can see some different examples up here in the upper right. But the main thing would be when you're using these ferrites, there are different kinds in terms of the frequency that they're effective in. Make sure that you're selecting one that will help in the area that you're having trouble. That's the main thing, but they are very useful for identifying the common mode noise and helping to see if that makes an impact in your measurements. So here's some examples of the field probes. On the left, we have some of the H and E field probes that are kind of in the middle range of cost. You can connect them up to oscilloscopes. This one's shown with a BNC, but obviously you can adapt it to a spectrum analyzer or any other type of input connection. And this would be more of the specialized current probe on the right-hand side here. Would typically be used with a spectrum analyzer because they're measuring more accurately than an oscilloscope would. So just some real quick basics on EMC. So a moving charge generates an electromagnetic field. That field could potentially induce a current. But if we have these things, these charges moving past one another in opposite directions, they're going to create fields that will cancel. And that's where we want that type of setup in our system, and that way we'll have lower emissions. If we apply that electromagnetic field to a conductor, free charges can move. So one of the things that we'll take a look at later on is if we apply a field to a conductor, we can create movement and charges, and depending on the path of least resistance, those charges may go places we don't want them to go, creating common mode noise and showing up in our radiated emissions plots. Rise and fall times can affect frequency, content, and amplitude. Francesca touched on that a little bit. This is based on just kind of a worst case simulation. I made things as bad as I could make them and did a 5 nanosecond rise time pulse versus a 10 nanosecond rise time pulse for an off battery buck converter. And it can be 100 times difference in terms of the levels at 100 megahertz. That's pretty significant. In reality, it probably is not going to be that high, but in this worst case simulation I put together, that was the difference at 100 megahertz. So I like to throw this in there just to think about how we either impede the path of electrons or create a lower path, a lower resistance path to the way we want them to go. So the drift velocity of electrons in an 18 gauge wire with 1 amp of current is 74 micrometers per second. So that means in a 3-hour trip in your car, an electron that leaves your battery may not make it out of the engine compartment. So electrons are generally lazy. If we impede their progress, they don't want to go a certain way. If we give them a path of least resistance the way we want them to go, they will go that way. So kind of how I like to think about how electrons move. From an emission standpoint, 20 dB microvolt is 200 nanoamps into 50 ohms. So that's very low current. That's all it takes to fail in some regions, and even limits may be lower depending on the band you're looking at. If we think about that in terms of immunity, that same 200 nanoamp current in a 1 mega ohm ends up being 0.2 volts. So this is particularly interesting because if we have a feedback network setting the voltage on our converter, if we use relatively high resistance values to set that, let's say one of our design criteria is for low IQ, but we have a fixed output or an adjustable output, excuse me, we may have to use higher impedances to limit the amount of current that's going through that feedback path. The unintended consequence of that might be if we have some noise that comes into that feedback path, it's going to mess with the output setting, and that's where the immunity comes in. Overall, if every charge that leaves that battery in the EMC chamber comes back in the shortest, smallest path loop, it will be a boring day in the chamber. Obviously, that's what we're all hoping for. So real quick, just in terms of charge case 1, this is kind of what we want to have happen. We have charges moving towards our circuit down the power lines and coming back. We want equal amounts of that, and then we will have very little emissions. That also includes on our board as well. Case 2, we have different amounts of charge moving in either direction. So this is going to be differential, and we're going to end up with some amount of emissions depending on how much charge at what frequency. Case 3, so they're traveling in the same direction. So this is common mode, and this is also going to show up in our radiated emissions and cause potential problems. And this is basically things leaving the board and having to come back and find the best path back to the return. In case 4, we'll show basically equal charge, but we've got path length being different. And this is this loop kind of scenario. Maybe imagine vias in here where we have keep outs where the electron on the ground plane, for example, may not be able to take the shortest path back, and it takes a different path and we have a bigger loop. And that's also undesired in our EMC world. So also going to take a look at the areas of interest for us. Francesca's touched on this a little bit. I'll show some of the waveforms. So from a buck converter, I'm showing the switch node here in blue, and we've got this high DVDT, right? So from an off battery perspective in automotive, whether it's 12 volts or 48 volts or whatever the case may be, we've got that much voltage switching in a short amount of time, right? This DT is typically nanoseconds, and it's something we're going to trade off in EMC for efficiency, right? The quicker we switch, the better our efficiency will be, but we may have, or we will definitely have more energy content at higher frequencies. If we switch slower, we'll have less energy content at higher frequencies, but we'll also be sacrificing our efficiency. On a buck converter, our output current is continuous. It has this triangular shape that Francesca talked about earlier as well, but the output current is continuous. And I'm kind of assuming some nominal load here, that we're not discussing discontinuous mode, for example, or a light load mode. On a buck converter, the input side is kind of our problem area. As you can see from the waveform here, the input current is very much discontinuous. So we have high DIDT on the input side. When Q1 turns on, we're supplying high amounts of current and we're ramping through the inductor. And when it shuts off, we'll see in the next graph the current through Q2. But we have this current through Q1 basically with high DIDT. So it's turning off, coming to 0, and then it'll switch back on in the next cycle. For Q2, it's kind of the opposite. So after Q1 has shut off, we're going to recirculate the current for the inductor through Q2. So we see this high ramp up of current, and then it starts to decay, and then it shuts off, Q2 shuts off, and we'll turn Q1 back on, and we'll start this process all over again. But we do have that high DIDT on the Q2 side as well. The return current, we want to pretty much be a mirror. And if we have the exact opposite, so to speak, current from I out of the converter on the return current, we're going to be in pretty good shape as long as that loop is small. The input capacitor, which is what we want to be supplying the circuit ultimately, you're going to notice that that current goes from positive to negative, right? So what we're going to have here is the vehicle battery charging this up, and then we're going to be supplying current to the buck converter and transferring energy into the inductor. So that you see this high DIDT show up on the CN capacitor as well, and that's why the placement of those are critical, as Frances talked about. So we have this high DVDT on the switch node, especially off battery, right? If we look at a post regulator, and we will look at that a little bit later, this DD is pretty high for off battery versus a post regulator. This is much smaller, and the DT, if we keep the same, it's just going to be relative to the change in voltage. And then we have the high DIDT on the input, both on the high side switch and the low side switch. And so when we're talking about boost converter, we'll take a look at an example of a boost converter later, but it's basically just the opposite. So we kind of flip everything around, move our switch node over, and we have the same waveforms. They're just respect to the other side of the inductor, so to speak. So we've got CN, which is continuous. So we're either supplying current through the inductor, charging it up, or we're letting that energy flow to the output. And the waveforms are just the opposite of the buck converter. But we still have the same problems. We have the potentially high DVDT if this is an off battery boost, as well as depending on the output voltage. And then we also have the DIDT on the output side. The current in a boost converter is discontinuous, whereas again on the input it's continuous. This is a very simplified diagram of the test setup for different different frequency bands, whether it be for low end or high end. What we're trying to show here is the path that we may have from our DC to DC circuit through the straight capacitance to the ground plane. This energy does want to make it back to the board, and that's where it ends up showing up as common mode, coming back through the cable back into the system to get back to where it came from. So that's going to show up as common mode noise in this particular case. We do have some numbers on here. Taking a look at the different limits and different OEMs, the numbers may change from region to region, band to band, OEM to OEM, but 12 dB microvolt is 4 microvolts at this listen. So if we have that kind of energy that's making it this way, it's not going to be good for EMC. So that's 80 nanoamps of current. The buck converter at 13 volt input at 2 megahertz, we're looking at about 260 millivolts at 100 megahertz at the switch node. So this is what we have to deal with in an effective manner to keep that from showing up. So identify the source, looking at kind of, we've got some measurements and we're taking a look at them. You know, how do we start this debug process? So we need to identify the source. Sometimes it's pretty obvious, right? We've got a very repeatable noise source in this plot, right? And if we look at it, there's essentially 8 peaks in this 10 megahertz band. So something's clearly going on at 1.25 megahertz in our circuit. Is this the fundamental of our DC to DC power supply? In automotive, that typically wouldn't be the case, but clearly something is going on at that particular frequency. Or we may have the case where it's very broad and spread out, and it's not a particular frequency that's giving us trouble, and we're going to have to take a deeper look at that. So one of the things that we can do in design and in troubleshooting when we get to having a failure is take a look at our system and all the clocks, both the switching frequencies of DC to DC power supplies and any other clocks, and how they might interact. You know, when we get to layout, perhaps we have one of these sources close to another, and we end up with a mixing product showing up. Here I just have circled 102.595 megahertz. So that's a pretty odd frequency. But if that shows up in your EMC signature, you know, where is that coming from? You may not have that particular clock, but that could be a combination of your 20 megahertz oscillator and your 489 kilohertz switcher. So where could that possibly be mixing together? So you can use this sort of approach to narrow in on what is going on if you have a very particular frequency showing up in your EMC signature. Another thing that you can do is try and find the path. In this particular case, we're looking at a rather small system, right? If you have small boards and small products, the potential for coupling kind of increases and bypassing some of the countermeasures that we have in place or design that we have in place. So typically we would have a differential mode filter on our product. And if we change those values, so we already have some EMC results we're failing. If we change those values, we should see a corresponding change in the EMC data. Now, when we're looking at the input filter, typically that's going to be in the lower frequency range. Typically inductors and things like that stop becoming inductors when you get into really high frequencies. So if we have issues at the lower frequency and we change some of these components, do we see a corresponding change in the emissions? If not, we need to think about why. So what is the distance between the buck C-in and the filter, right? So now, are we seeing some of that coupling from our converter and it's bypassing our filter? So in this particular case, this picture, we're showing, we've taken the filter off board. This is kind of hacked together and we're moving the filter further away from the converter. Does this have an impact on our radiated emissions or conducted emissions? If yes, then we might be bypassing our filter altogether and we need to figure out how we can stop that from happening. So here we're showing an example of a large board with multiple power supplies. This can have its own set of challenges. You can kind of see we've got different power supplies spread throughout the board, and even over here we can see different sections of power supplies and things like that spread across the board. Are these things interacting, and how do we keep them from interacting? So one thing to keep in mind, if this particular diagram is showing a split off battery approach, and this could be for many reasons. We have an always on system, or we have different high power sections or things that we want to keep separated. So we're showing 4 off battery power supplies in this case. So here is the input filter for the overall system, and then we've got 12 volts coming into each of these guys. If we just assume, for example, buck 1, 2, and 3 are all switching out of phase, so neither one of them is turning on at the same time. We're not synchronizing the turn on event of these guys. We're going to have a high DIDT event here at the input of buck 1. But because we only have very, very small resistance and an inductance between the output of this filter and the next stage, we really don't have good way to control where that charge is coming from and going to necessarily. So what could happen, depending on the impedance of these paths, is we could have energy from buck 2, its input capacitor, going to supply the CN1 that then goes into buck 1. And this could be based on geographical location, right? So if buck 4 is further away than buck 3, we're just going to have a slightly more impedance, and it's going to want to take energy from buck 3 or buck 2. It just depends on the location on the boards. So instead of this filter, the output of this filter supplying each of these guys, we've got each of the bucks potentially supplying the other bucks. And that's, again, just according to how much is impedances between each of these different sections on the board. This may potentially create coupling in other circuits depending on the routing and other aspects of our design. We can also think about this. We've now inserted an off battery supply, and we're going to point of load power supplies. So we've got a 5 volt or 3.3 rail, and we're supplying 1 volt, 1.1, 1.8, different rails we might need in a larger system. We can still have this sort of phenomenon where the bucks are still providing energy back to one another and having currents flow in directions we don't necessarily want them to. So the way we can do that is just add some impedance in between each of these guys. So now, knowing that electrons are lazy, because we have some resistance going back this way. Buck 1, when it turns on, it's going to want to draw all of its power from CN1, and then we're going to allow the battery, in this case, we've taken out that intermediate rail, allow the energy to resupply it directly. So as long as we have some impedance between these guys, we can keep these guys separated and keep their input capacitors providing energy to their bucks specifically, and no other bucks. So now we'll get into some examples. So this is the 43XX series. So we're looking at, in particular, a 5 amp out at 2 megahertz. So just some highlights of the schematic here. On the top section, we have our standard pi filter. We have a magnetic bead, but I'll talk a little bit about that. Francesco also touched on that a little bit as well in his previous presentation. We've got our standard pi filter with our aluminum electrolytic here. And then we go down to the input of the buck converter, and we have our local decoupling caps drawn in parallel. Obviously, that might not be electrically the case on the boards. We need to be careful about the layout of these capacitors. Our 1 microhenry for the 2 megahertz switcher, and then we have our output capacitance shown here. This particular device has a frequency pin that you can select your switching frequency based on the resistance out here. And we also have our bootstrap power supply. So this is to provide energy to switch the high side N channel MOSFET. And in our EVB, we typically do have placement for a boot resistor set to 0, generally on our EVBs, but it's there just in case. So I'll talk a little bit tomorrow about this as well, but we have the input filter on the bottom side, and I'll talk about that a little bit later in this presentation as well. So our input filter that was shown on the top section of the schematic is on the opposite side of the board here. And then Francesc talked about the split of the input, right? So we have our bulk aluminum electrolytic, we have the routing on the inner layers, and then we come up on either side to the first ceramic cap, and then the high frequency cap, and then VN. And so this is symmetrical. Trying to create equal and opposite currents. It's probably not going to be absolutely perfect, but then we also have the parallel combination of these guys. These guys will truly be in parallel in this particular configuration. We'll talk a little bit about that later as well. Here's the inductor with the switch node. You'll see in this particular case, this is a 5 amp, so we have a little bit bigger inductor, and we're putting ground underneath the inductor, and then the output side with the output caps. So real quick, just to think about how the energy is flowing, right? So in this T configuration, this is kind of just maybe a visual representation of what we have going on, right? In this particular case, we can get charge on either one of these capacitors because it's located at the same place on the supply trace, and it's also directly on the trace, right? So the amount of impedance that each one of these has to this trace is going to be roughly the same. If we then think about this condition where we have the aluminum electrolytic and then all these different caps, the charge is going to want to go from one to the next to the next to the next, because in reality, we have a very, very, very small resistance and impedance here that makes these somewhat separated and makes things kind of flow in series, more like this illustration below. So not exactly, but this is kind of how I like to think about the charge flowing and why we do recommend some of these different layout techniques where we can have more of a true parallel configuration versus these are parallel on the schematic, but on a board with some parasitics, they're not actually in parallel. So here's that input filter on the bottom with that T configuration. And this filter, as we have it on the EVB, provides around 50 dB of dampening at 2.2 megahertz. So there are ways to calculate what you might need depending on what you see in your EMC results. And in this particular case, we're looking at changing that 1 microhenry to a 330 nano and reducing the capacitance as well. And we're getting about 33 dB. You can set up this kind of table. There are equations to do this. There are also vendors out there that have simulation tools. Murata has one on their sim surfing suite. And you can also do simulation as well. I talked about, I did some simulation on some filters just to get some numbers for this. We have a tool called MP Smart where you can do simulation as well. Both of the filter and the power supply, you can take a look at energy content, things like that. That's a full simulation tool from MPS. So in this case, now we're modifying the filter to see what the impact is. So we were calculating with this ferrite removed in the inductor, we're looking at 33 dB at the fundamental. And we also changed this 4.4 nominal capacitance to 470 nano nominal and kept the aluminum electrolytic. So doing some testing on that, we see that we actually have around 30 dB difference at the fundamental. So we're out here at 2 megahertz, and you can see we're right around 55 dB microvolt. And come down with the filter, we're down to 25 dB microvolt. So, you know, our calculations, at least in the initial few, the fundamental and the harmonics, that looks to be pretty good in terms of our performance. But then we start coming out here to the FM band, and we see that we're not doing so good. So we need to make some changes there. So one of the things that we looked at in this particular case was rotating the output capacitor 90 degrees next to the inductor. And I'll go into a little bit about that in future slides. We also looked at verifying the start of winding. So just flipping the inductor around anyway. This particular inductor does have a start of winding indication, but I'm going to show the results here. So this is the family of inductors. So it's a 5 millimeter square, roughly inductor at 3 millimeter high. This is that 1 microhenry on the switch node. And you can see here, the dark blue is with the start of winding away from the switch node, and the light blue is the start of winding at the switch node. And these are the peak measurements with the average below here. And it's still the same thing, start of winding away from the switch node and start of winding to the switch node. And it doesn't matter if it's a buck converter or boost converter. We in general want the start of winding to the switch node for best performance. So in this particular case, with this particular inductor, we're seeing 2 to 3 dB better performance in our emissions by changing that location of the start of winding. If we also then replace the 5030, which is a 5x5 3 millimeter, with a 4x4 2 millimeter high inductor, and likely we're making some trade-off with the saturation current of the device or of the inductor. The smaller coil is better by 1 to 2 dB, 3 dB in some cases. It just depends on what frequency you're looking at. But the dark blue is the peak for the 5030, and the light blue is the peak for the 4020, as well as the difference in the average of those two inductors down here below. So smaller is definitely better. And start of winding, as mentioned on the previous slide, paying close attention to that is definitely a good idea. One of the things we'll look at on the next slide, so you know, this 10 dB line, we're roughly at 10 dB microvolts average at 90 megahertz here. With a 2 megahertz system, typically the input filter isn't going to have a huge impact on what we're doing out at these higher frequencies. And one of the things that we have to look at is the amount of energy content we're putting into the higher frequencies. So what we did on this next trial was add in a 4.7 ohm boot resistor. So that's going to slow down the switching of the high side. And now you can see where we were at 10 dB at 90 megahertz. This is the old data. Now we're all the way out to 108 on the first set of bands, and we're still below 10 dB microvolt. So there are some trade-offs in terms of switching frequency. Obviously, if you start below the AM band, you have to deal with the fundamental and the energy at that lower side. If you go to 2.2 megahertz, you're going to avoid the AM band altogether, but you're more likely going to have some other issues out here, potentially, depending on layout and things like that. So typically, you're just moving the energy up in frequency at when we decided to start at 2.2. So here's another example. We have a 4314 providing a 3.3 volt output, and then we're using a 3.3 to 5 volt post boost part. And I'll make some comments here that maybe this loop is probably not the best idea. Oops, excuse me. Maybe this loop that the load resistors form and these wire connections may not be the best. But we'll go through the data anyway. So from the switch node perspective, whereas a buck, we used to be switching on this side of the inductor. With the boost, we're now switching over on this side. And we're either providing energy to ground or to the output, right? So our output current is now discontinuous, and our input current to the inductor is continuous. Our dV dt is over here on this side, close to the converter. And then we have to worry about our di dt out on this side. So you can see what we did. It's been removed in this picture, but we were providing power off board. So we put a filter in here of 330 nanohenry with a 1 microfarad. And we were also changing to the symmetric layout of the capacitors. I have a picture showing what it looked like before, but essentially it was more of the eye or straight line configuration on the capacitors. So we tried these things first, and there was no effect. So now what? So this is the picture of what the cout configuration looked like before modification, and this is after. So trying to create everything in parallel here. What we did is change the inductor next. And what you can see here is we have a 4x4x2 is this original inductor, and you can see the start of a winding going to the switch node. And we replaced it with this MPL AT 2010. So this is a 2x2 1 millimeter high inductor. Obviously, with the smaller size, there is going to be some trade-off. This particular boost is only, I think the peak current limit is about 1 amp, so it's not going to be providing tons of current. So this is probably overkill, but the DCR is pretty good. So we're getting a little bit higher DCR, a little bit lower saturation current or RMS for the temporize, but this was the idea. Let's change this and see what we can do. So you can see here the limits from the original coil. They're about 7.5 dB higher in some cases, actually 10 dB higher in some cases. And this inductor change is making a significant difference, both from well, I'd say mostly from a size perspective. And Francesca touched on it, and we'll go into a little bit more detail about that here. So power inductors are not all the same. We do have these flat. Oops, excuse me. I don't know what happened there. So we do have the flat wire construction, either stacked or wound around the core. The wire type, they're not all constructed the same. They're not all shielded. Some are semi-shielded. Some are say they're shielded, and they're shielded in different degrees. So you're going to have to kind of investigate that either with the inductor suppliers or kind of go with some best practices or things that you've learned along the way. Again, in terms of what was discussed previously, both the start of winding is important and the size. Typically larger inductors tend to have more antenna space, and we'll take a look at that as well. So just looking at different inductors, we've got this 10 by 10 inductor from, I believe this is Worth, and not necessarily that this is a bad inductor, but there are just differences in terms of inductors, right? Here's between a very particular power supply. We've got from 22 dB microvolt to 6 dB microvolt, just from changing the inductor. So the construction and the inductors do play a very big part in coupling into other areas of the circuit. Right, and even in this particular case, we have an EPCOS with a manganese zinc core, and we're looking at the start of winding at the switch node versus not. And in this particular case, with this particular core on the inductor, we actually see 6 dB difference worse with the start of winding at the switch node. And this is something that we're investigating, but we think this is because of the difference in the core material. One thing I'd like to note is this is not an automotive rated inductor, so maybe in automotive this won't be such a concern, but typically start of winding should go to the switch node. But in this particular case, with this particular inductor, that's not necessarily the case. So when we think about the inductor and the impact it can have, right? So if we're going to make a good radiator, we want to send energy off into space. We either have cell tower or TV tower. Is this a good radiator, right? It's above the ground. We're sending the signal out. This should be good. Well, what about now? What about when we start putting buildings around it? We stack them higher and higher and higher. Is this becoming a good radiator? It's no longer a good radiator because we're blocking a lot of signal content that's coming off of this antenna. And that's kind of the same principle that we have going on with the inductors, right? When we have these huge terminals or metal clips on some of these inductors, this does have that time varying signal on it. And we're now providing a path for that to get out because we're raising it above the board. We have that TV antenna effect. And so this becomes a very good antenna. Very good is relative, right? When we're talking about, is it ideal for the frequency we're trying to transmit? Maybe not. But even if it's not tuned to that specific frequency, it still can become an antenna. We're still applying that time varying signal to it. So we have to be very careful with how we do this, even when the start of winding is to the switch node in this particular case. And that is the way it should be for this particular inductor. So how does that look in terms of a board? So this is just a 3D representation, right? We've got an inductor with this metal clip up here, and it will act as an antenna and could potentially radiate and be picked up by other areas. And if this energy bypasses the return path, which would be first to this capacitor here and then back, this is going to end up showing up in our radiated emissions plots. And this is actually a design we'll take a look at tomorrow, where I've actually replaced this inductor for the 3D model, but this is not the inductor we use. And there's trade-offs that you're going to make, right? You can easily optically inspect this inductor. Other inductors you may not, but it might not be the best fit for your design depending on the size and other design constraints you have. So if we then take that one step further, instead of looking at it from a theory perspective, we had a colleague do some surgery on this particular inductor, and we removed that metal clip. So you can see that metal clip over here. That's now been removed. We've added a ground strap here because we've kind of destroyed any amount of shielding that inductor had previously, trying to do surgery on it, so to speak. And what we're seeing is when we tie that start of winding directly to the pad, instead of having that big, tall clip there, is we actually have 6 dB lower emissions at a megahertz in the monopole test, right? So this clip is acting as an effective antenna. And I mentioned previously, we had looked at rotating output capacitors around by the inductor. What we were trying to do there was to create those tall buildings, so to speak, where we would have this ground connection where it could be blocked, that radiating antenna could be blocked by the capacitors. So that's one thing that we tried doing in that particular case, and something that you can do. Try and block this antenna from being effective at all in terms of bypassing any amount of filtering or having energy go somewhere we don't want it to go. So these are the test results. So you can see these are peak measurements, and blue is the original inductor, and pink is the inductor we did surgery on to remove that metal tab. And you can see the difference. It's in this particular case 30 down to 23 dB, so 7 dB difference at the fundamental of the switching power supply. And the other thing I'd like to point out, these particular results in this power supply, this is being done without spread spectrum, and you can see that because this is very distinct frequencies. It's not the spread out version that you would see with spread spectrum. So if we needed to pass EMC, let's say we were failing further out, one thing might be to take a look at that inductor. Another thing might be to add spread spectrum, and that's all the variation you might need. Here's the average results, kind of the same story, 6 dB difference. So we were over this limit line here previously, now we're below it, just with the different inductor or the different mounting method, removing that large tab. So one last example, this is going to be on isolated power supply. So in this particular case, you can see that our input filter seems to have no effect on what's going on. And we see these very specific frequencies coming out from the converter. So what are we going to do? And this is actually a good example to walk through, because we were going through everything, right? Snap-on ferrite for common mode, no improvement in this particular case. Let's test it with off-board EMC filter. Maybe we're bypassing that somehow, and noise is coupling in through a different route. No improvement. Copper foil around the circuit, there is some improvement. We added a Y capacitor between the primary and secondary ground. Again, this was an isolated power supply, so each side's going to have their own ground, and this was showing a strong improvement. Another thing we can take a look at is, again, it very much looks like we have on the input filter side kind of the I configuration instead of the T. So you can see that we have identified some other layout changes and things like this that we're going to implement on the next board revision. But this is kind of the methodology, and I thought this would be a good one to show, because we don't always jump to the right conclusion ourselves. There is that process, and obviously adding this particular Y capacitor shows that there's some interaction in the grounding. So if we have energy coming from the secondary side back to the primary when it's not supposed to, we need to find a way to get that path blocked, or we need to get that energy back to where it wants to go through the path of least resistance. So just to wrap up here, some points on what we talked about. Check the EMC structure for effectiveness. If you're at low frequency, you can change the values of those filter components, and you should see a corresponding change in your emissions data. If you're not, then your filter's not being effective. And we may have to take a look at that. Move the filter off board and hack it in if you can. Add a common mode choke or the snap-on ferrite to take a look at that. Review your PCB layout for high DIDT nodes. Make sure the loops are minimized. We're not breaking up the ground. We've got very good placement of our input capacitors on bucks and outputs for boosts, switch nodes minimized, things like that. For the high DVDT, same thing. We should have very small switch node and low profile. So smaller parts on that DVDT are going to help with preventing that noise from radiating out and coupling into other areas of the circuits. Try different inductors. Try smaller ones, try lower profile ones. I know it's not always possible for optical inspection, but try inductors with connections on the bottom side and see if that helps. And check kind of the distance between parts, right? And we'll take a look at a design tomorrow where it's one-sided in terms of component placement, but if we have a very, very small board, and I have a customer that designs stuff that's essentially like maybe 2 inches by half an inch wide or 1 inch at best, they do have to use a shield because everything's so small, everything's so compact. They can't avoid that coupling from the switch node back to the input side. So they have to basically contain it with a shield in the design. And this particular customer says that shields are cheap and they use them on everything. So it just depends on the product you're building and what your issues are. Space is a good one, and we showed the different size of the inductors. If your module is very small, you're going to have that kind of coupling. So these are things that you may have to keep in mind with in order to contain that energy within your system and get it back to where you want it to go without bypassing any other the shortest return path. So that's all I had for this session. If we have any questions, happy to take those now.
Yeah, and it looks like we've had a handful of questions come in while you were speaking, Mark, so we can just jump right into those. The first one was for the frequency table that has F1, F2, F3. I noticed there was I believe it's an F3 minus F2 or F3 plus F2 missing. And the question was just, is it just because the table needed to be small for the presentation, or was there a practical reason?
I think this is just a snapshot. Ideally, you want to expand it as much as you can. These multiples, as we get out here, we should be seeing less and less energy, and generally you're going to see it cut off. Oops, maybe around 5 or 6. It's going to depend on your system, but making sure that we expand this out, because this can be an aha moment. I've seen this before with a particular system I was testing where there was a very standout frequency. So yeah, making sure that this table is expanded out as much as possible will help. And you should have the different variations of the frequency. It's just, it depends. When you get to the layout, if none of these things are near each other, you're likely not to have any coupling and you won't have any mixing products. But if you have a SPI clock or a DC power supply that ends up, the switch node could couple to something else, it's possible that you end up seeing some of this.
Very good, thank you. Next one, does the boot resistor, if added to slow down the switch speed, what is a practical limit so the device doesn't become unstable?
Yeah, that will depend device to device. I would say in general, I wouldn't go any higher than 20 ohms, but it's always best to test in your given application with that. 20 would be a general rule of thumb. I've actually seen applications where we've gone as high as I think it was 40. It was 40. So beyond that, you're going to run into trouble. But whatever value you do select, make sure that you test with it. Something that's below 10 ohms, I think is very would be safe. But again, just make sure that in all conditions it's able to be stable.
Okay, and then next up we have, what is the significance of the capacitor footprint size, assuming smaller sizes meet the voltage requirements? And then asking about the specific sizing, and then do larger capacitor footprint sizes have better EMI performance? If so, how much? Capacitor companies push to utilize smaller sized capacitors.
Yeah, it'll definitely be it depends. So if we take a look at this particular layout, the smaller capacitor sizes generally have smaller parasitic elements involved with them. So the ESR, the ESL, but they're not going to be able to store as much energy for a given case size. But those smaller parasitics help us with lower impedance to ground, in particular on the input side, just looking at this particular case. Right, so these will perform better at higher frequencies because of that. And if you take a look at the manufacturer's information on that particular capacitor, they should show you like a Z versus frequency plot. And sometimes that's a way to help you select which components might be of use to you if you're trying to target very specific things. This tends to get into power integrity discussion and things like that, but typically smaller is going to be better in terms of parasitics and its performance at higher frequency. Larger is going to be more towards the lower frequency side in general. I did show that one example where we were rotating the capacitor to try and act as a shield on the switch node, right? So in that case, we maybe wanted a taller capacitor because then it would match more of the size of the inductor and its connect the plate, the vertical plate that goes on the inductor for the optical inspection and then the connection. In this case, bigger might be better, but when we're looking at the things, the capacitors for frequency, typically smaller is better for the parasitics.
All right, and then we had regarding the inductor selection, I find that SRF is a useful figure of merit to consider. Once I've sorted for a range of acceptable DCR, saturation current, and the like, I sort for the highest SRF next because I want to minimize parasitic C between windings, which translates to less high frequency bleed through the part to the output node.
Yeah, that sounds like I think that's a comment, but that's a very, very good comment. Without pulling up one of the other plots, but we can look at this range because typically the SRF is going to fall in this range anyways. Some of the higher inductors, they might go out beyond this. So like 1 microhenry and lower. There are some high-end inductors that go out beyond 108 megahertz for SRF, but whoever made that comment is right. If we have an inductor that behaves more like an inductor over a wider frequency range, it's going to be better at acting like a filter in our application. So having that would be very beneficial.
Okay, and this next one's a little bit more of a not really so they're requesting to show the schematic for the Y cap in example 5.
I don't know if I have that handy, but I can certainly I can follow up offline with that.
All right. And there's another kind of a request for example. High dV/dt area should be small and low profile. Can you show another example? Specifically what is meant by low profile. So not sure that, again, that's something we have in this presentation.
Kind of, sort of. And I'll have more on that tomorrow, where actually this example, there is no terminal here. There's inductors that have the mounting only on the bottom. So this metal tab isn't here. This particular inductor is relatively high, right? It's that tall antenna compared to these guys. Whereas when we look at let's see, that would be the results of the 50-30 versus the 40-20. Go back to that. Yeah, so this is the difference between this particular inductor is a 3 millimeter high versus a 2 millimeter high, and we are making some trade-off in terms of the saturation current of this particular part, right? So it depends on what your application really needs, and I'm willing to bet that the DCR of this part is higher than the DCR of this part, potentially. We have to look at it. But this is the difference between a smaller inductor and lower profile. And in this particular case, this inductor, without looking at it, I'm pretty sure it has the mounting terminals on the bottom anyway. So even with the mounting terminals on the bottom, the smaller inductor still is 1 to 2 dB better in this particular example.
Okay. And then again, looks like more of a comment, but if you want to comment on their comment regarding cap size choice, something really important to remember is that larger size caps show reduced DC bias effect, loss of capacitance as a function of applied voltage.
Yeah, that is absolutely a key design criteria when you're looking at this stuff. Typically, go back to the full schematic here. Typically, what you're going to see, so these are like 1 nano, 10 nano. These are 0603s, but a 2.2. We don't have the case sizes listed there, but these particular components will be larger based on the voltage rating of the capacitor. And typically, the larger the parts, the larger the voltage rating possible, and the larger the capacitance as well. If you have, let's say, on our 5-volt circuit, if these are 6.3 volt rated parts, you may only get a third of this 22 microfarad value, and that's impacting both the ripple on the output as well as potentially EMC. I mean, that could very well affect over here, right? That's going to change the frequency at which these guys are effective. So making sure you have the right case size and voltage rating and nominal capacitance selected are very important. And generally the vendors for the capacitors will either have that information listed directly on their website or available to you, and you definitely need to check the DC bias characteristics of the capacitor you're selecting.
Okay, I think that took care of all of our questions. If we have any final ones, put them in right now. But again, thank you everyone for your time today. Hopefully you got a lot of good information that'll help you out with your designs. We will be back at the same time tomorrow. Again, we'll have 4 engineering sessions covering spread spectrum, radiated emissions, and then Mark will be back again tomorrow covering 2-layer PCBs. So a lot more good stuff to go. I seem like I've gotten the question many times, but yes, we are recording these sessions, and you'll be able to find them at monolithicpower.com/webinars. We will email them out if you directly registered for the sessions. Please note that tomorrow's session is a different access link. So if you have not registered for both sessions and gotten the reminders to those, you might want to go back. There's a feature right on the homepage of monolithicpower.com to go back in and re-register. But again, thank you for your time and look forward to seeing you again tomorrow. And I didn't see any other questions come in. So with that,